Hello, thank you for the introduction. Hi, I'm Ayoung, and I will present the paper Computational Hyperspectral Imaging with Diffractive Optics and the Residual Network. Let's start with the content goes like that from the problem, existing method, and what we proposed in this paper, and then simulation results and conclusions. First, the problem. There is two different big problems. First, how to capture the hyperspectral data cube, because as you can see, the hyperspectral data cube consists of 3D data cube, which includes two dimensions for the spatial domain, which is notated by X and Y in the picture, and the lambda, it denotes that spectral domain, which can be the continuous or discrete. I'll discuss more about that later, but how to capture this 3D data cube with the conventional camera that contains 2D sensors. So that in conventional way, they try to capture in scanning method, which means that it captures along one axis of this data cube, X, Y, or lambda, and then they accumulate the measurement and reconstruct the 3D data. But in that way, it consumes lots of time and several capturing is required, so it is not even practical for the dynamic scenes because scene is changing, but we need to measuring several times. So that the new method came out, which is called snapshot imaging method, which wants to capture whole data cube within a single detection period. And it will be shown in the next existing method area. And then with that snapshot imaging method, it caused the ill-posed reconstruction problem, which is the second big problem of hyperspectral imaging in general. So the existing techniques about one of the most famous and widely used snapshot method, which is called the coded aperture snapshot spectral imaging, so-called CASI. And as you can see, it contains lots of optical elements, which is like 6 to 9, depends on the CASI method, and it is quite bulky to use in practice. And more importantly, it has some trade-off between the spatial and spectral information. So this is using the amplitude modulate, but what another method comes out for substitutes this method is modulates phase information of the signal so that using the diffractive optical elements can replace all those bulky optical elements inside the purple box so that it is very compact form of hyperspectral imaging with the optimizing DOE patterns through the fully differentiable simulation model. And another part of existing techniques is handle about how to reconstruct the 3D data cube from the single capture in the snapshot model. There are two different categories. First is iterative optimization method, which is very effective for releasing the ill-posedness, but it requires exhaustive parameter tuning, such as like step size, how much iterating numbers would be, and so on. So that the deep learning method make it a big revolution for that because it could improve the spatial and spectral quality, but also it could be done all the optimization within way shorter time. So the proposed method is using the hyperspectral camera model using the diffractive optical element, which is very compact, with the deep learning method, which is called the residual dense net in this case. As you can see, there is the hyperspectral cube, and we want to capture from the camera, and then the captured image is the 2D image, which contains, you can think it as like grayscale image, and then it will be reconstructed to the hyperspectral cube through the residual dense network. And from backpropagation, it updates the network parameters, but also in the camera parameters, such as the diffractive optical element pattern and the color filter in this case. So in detail, how the camera model looks like this. First, there is, well, it seems the equation is a bit lifted, but well, maybe it's readable. And yeah, so first, we start with the continuous camera model because it is reflecting the physical model of the camera. But in practice, we were using the discrete camera model because the point spread function of the DOE and the color filter function kappa is updated through the pixel sampling, so that's why we use the discrete model, but there are the benefits of discrete model. First, it consumes less memory to saving all those data cube information, and also it makes a faster computation. Lastly, the application called remote sensing image has very sparse information in waveform domain so that they can compress all those signals if we use the discrete model. So in detail, from the lens domain, we updating the diffractive optical element pattern, which is noted as phi in this equation, and then from sensor domain, we updating the color filter so that the color filter function is noted as kappa, and it is marked as purple because it is one of the optimizing parameters. And in our reconstruction network, which is called the residual dense network, looks like this, and it consists of 4 different parts. First part contains 3 by 3 spatial size convolutional layers, and then second, we use densely connected feature extraction layers so that it requires less depth or complicated structure for the extracting features. And then at here, the concatenate is combining the features extracted from each layers before that, and there are the reconstructed part for using the convolution layer. And we pick the loss function as L1 loss function, which is sparsity induced loss, because it is very useful for reconstructing the sharp image in many image processing applications. And in general, this residual dense network, which is using the residual learning mechanism, is good for the better feature extraction, and also it has benefits of long-term memory, which connects the first layer to the last layer directly, so it preserves the original information from the beginning. So next part is about the simulation results, how well our method works well. In this case, we use KAIST dataset for training and ICVL dataset for testing. And this is one example of the ICVL test scene. And in general, on most of the scenes, our method shows the best results. And for visualizing the reconstructed result, I put the RGB image, which is weighting each spectral channels, but those PSNR and SSIM values are calculated in hyperspectral domain. And as you can see, that our method shows the best spatial reconstruction with the less blurry and less color artifact. For example, the SCI shows the quite strong the color shading, and the chat all shows the color operation if you see in the small cropped image around the edge part of the bridge. And the color also shows that our method shows quite good color reconstruction, such as in the sky, if you compare it with the ground truth image, and the rightmost figure plot also shows that our method have good spectral reconstruction. Second part of the simulation is about effect of DOE and the color filter. In this case, there are three different assumptions. First is using both DOE and color filter. Second is there is no DOE, but there is the color filter. And the third case is there is DOE, but without the color filter, which means that without DOE, which consumes that the DOE is fixed as the zero in the height, for the height map values, and without the color filter means we set the color filter is fixed as 1 to transmit the whole information of the spectral information. And we train them, each of them in fully end-to-end manner, so we get the optimized DOE height map and color filter for each case. The effect of the DOE and color filter shows like this. As you may see that the color filter affects a lot for reconstructing our method, but reconstructing good result, good quality in our method, but we can also say that nevertheless the DOE affects for the optimized results. And lastly, the effect of the phase and the sensor noise. Phase noise is added to the height map because of the fabrication, and the sensor noise is added to the captured image. And both methods are using the Gaussian random noise with the phase standard deviation of those different values for each networks colored by different colors, and the black color shows the network trained without any noise. And as you may see, if the noise is up to like phase standard deviation 30 nanometer, which is around the middle of each subplot, and the sensor phase noise until the 0.005, which is the second subfigure, our network without any noise shows the good result. But if there is the high noise environment, then better to train with the noise, so that in the last subplot you can see the black one gets lower than the red and the blue color plot. So in conclusion, a snapshot computational hyperspectral imaging system, which include the end-to-end learned diffractive optics and color filter array in the camera part and the deep residual network for the post-processing network. And as a future work of this paper, we suggest that utilizing the other post-processing network for enhancement of the result, but also we can consider different camera model. And lastly, we suggest we are working on how to fabricate those DOE and sensor color filter array as a real camera and test on the real image in the real world. Thank you for the listening, and any questions?